Welcome engineers, Hassan here. Today we are talking about scientific notation. Scientific notation is a way to represent numbers, large or small, in a concise and standard manner. For example, instead of saying 2,500 or 2,500 or 2,500, I might express the same value as 2.5 times 10 to the power of 3. Or if I wanted to write a small number, say 0.0025, I could write it like this. As you have probably noticed, we express a magnitude of the number by 10 to the power of some exponent. In this example, since the exponent is negative, we know that we need to divide 2.5 by 10 3 times to get to its original form. While here, we can multiply 2.5 by 10 3 times to get to its original form. Frankly, when we are talking about numbers of such magnitude, the scientific notation doesn't help much. But what about, say, power of 12? Would it be easy to write or read? Can you easily express it using natural language? How about power 22? How about power minus 22? Science is often concerned about things that are really big or really small. We human beings are terrible at naming things, and even more terrible at standardizing them. We live in a world with 7.9 billion people. Or are we? You see, I'm trying to say that there are this many people in the world as of today, in 2022. I have used the word billion. English is not my first language, not even the second one, so let me quickly check the dictionary. According to Oxford English Dictionary, a billion is a million of millions, or simply put, 10 to the power of 12. So, I guess I overestimated the world population by 1,000 times? However, I'm pretty sure you, my friend, are going to use the same wording I used. We need to talk about long and short scale. Up until the Second World War, the vast majority of countries were using this notion of the word billion as a million of millions. This naming system is called long scale. It was adopted by both English-speaking countries and the rest of the world. Two notable exceptions from this tradition were the US and France, which were using short scale, where a billion means 1,000 of millions. I'm sure that won't lead to any confusion among scientists in different countries. Basically, in long scale you have a million as a base and the prefix defines an exponent. B means 2, hence billion is a million squared. A trillion is a million cubed. A quadrillion is a million to the power of 4, etc. When using the short scale, you have 1,000 as a base. You may ask me, how come billion represents the power of 3 if the prefix b stands for 2? And I don't know, I'm just as confused as you probably are. The explanations that I've been given was that I shouldn't express it as 1,000 to the power of 3. Instead, it's 1,000 times 1,000 to the power of 2. Yeah. Anyway, before someone comes up with another brilliant idea on how to explain the short scale and long scale naming systems, let's bring them to the same base at least. We humans think in decimal. All we care about is the number of zeros, so why don't we use 10 as a base? This is now easier to comprehend, but having the same word meaning vastly different values, depending on what language you use and in some cases what regional dialect you use, let's just say scientists are not impressed. Instead, we could write this in scientific notation like this, and absolutely everybody in the world would understand this properly. If you believe communication and cooperation are important, you understand how vastly superior such expression is. Clear designation of values is not the only function of scientific notation though. It also simplifies arithmetics. Let me explain. Imagine you have to divide these numbers. The first thing you're going to do is to start counting zeros. Having faced with a problem like this, one would immediately come up with scientific notation or something similar. However, if we tried solving this with a long division like we were taught in school, we would probably get to the answer, but it's going to take a long time. Instead, You could write it like this, and using simple algebra tricks, you could simplify this in just a few steps. In case you need a reminder on algebra tricks, you may pause here for a second. So, you can simplify this by dividing the left and right parts separately. If we divide 10 to the 6 and 10 to the minus 9, we get 10 to the 15. Now we can divide 14 and 7 to get 2. Easy, right? In case I didn't convince you with my artificial example, let's take a look at the real-life problem. Calculate the gravitational force between Earth and Moon. Here is the formula we are going to use. This is not a physics video, so I'm not going into details too much. You may look up the mass of the Moon and Earth. Distance between them is changing throughout the year, but let's take the minimal distance. This way we are going to calculate the maximum gravitational force. Now we put our numbers into the formula and it looks like this. I'll admit, this looks scary, but in just a few steps we are going to simplify it. First, we simplify exponents with our algebra tricks and then we calculate the rest. In 3 fairly simple steps, we get to the answer. Congratulations! Scientific notation simplifies math, or physics in this example. However, not to rain on anyone's parade, we can still express the same number in several ways. And while some may argue that there is no difference, I beg to disagree. You see, while it is easy to do arithmetics with such notation, comparing numbers written in this way is not very intuitive. Wanna prove me wrong? Quickly, which number is larger? This is where standard notation comes in, also called normalized notation. Once we normalize our number, they become this. There is only one whole digit to the left of the decimal and it has to be between 1 and 9. Simple as that. And this does help with number comparison. Let's take this and normalize it. Now we can compare numbers at the first glance without doing any calculus in the head. The number with a larger exponent is larger, since the exponent corresponds to the order of magnitude of the number. In case exponents are the same, we just compare the significant part. E-notation. E-notation exists for one simple reason. Many devices or applications do not support writing superscripts, so instead we express the same value like this. Simple as that. To wrap it all up, let's finish with a formal definition of scientific notation. In scientific notation, we express a value as a product of mantissa and an exponent with a base of 10. Instead of writing many zeros or confusing denominators, we write mantissa and exponent. That's all there is to scientific notation. Leave your questions and comments down below. Thank you for watching.